Hello, my name is Chris Sievers, and I will be presenting on self-healing concrete technology, a state-of-the-art literature review. Let's get started. Uh, a little outline here. I'm going to begin with a brief introduction, and then we're going to talk about concrete repair, just typical concrete repairs, get a little background. And then I'm going to go over the seminal research regarding self-healing concrete technology, and then finally we're going to discuss the state-of-the-art of self-healing concrete technology and future areas of research. Moving forward, a little introduction here. I think we are all aware deficient concrete can pose a significant risk to public health and safety. We got to maintain it, and repair is expensive. Number two, we know deterioration of concrete is going to happen over time. It's inevitable. This stuff, it's exposed to the elements. There's weathering, there's heat, there's freezing, depending where you're at, abrasion, just a ton of things. It's going to happen. The best way that we know to stop it is to, or minimize the effects of deterioration, is to actually reduce the intrusion of water and other stuff, basically into the concrete. We don't want intrusion of chemicals into the concrete, which means that we don't want cracks, we don't want holes. So here's just two basic kind of typical, the main two typical types of repair that I'm experienced with, I've seen around. You either have your crack or you kind of have a deficient concrete section, usually like a honeycomb, something like that. Typically the cracks, you grout them out, open it up, and then fill with epoxy, basically to stop any water intrusion or other chemical intrusion into the concrete and avoid further deterioration. Same idea with the honeycomb there. We just chip it away using a jackhammer or a hammer and a chisel, and just replace the concrete with a no-shrink grout mortar. There's various products available to do that. Some of the advantages of self-healing concrete, obviously I just talked about the current state of repairs, but why would we need self-healing concrete since we already have methods to repair concrete? So obviously when we repair concrete, typically we're going to have two completely separate, different materials, different material properties, which is going to impact the performance of a repair over time. Obviously when you chip away the concrete or remove it and fill a crack with epoxy, that's not concrete. It's going to respond differently to the environment, and it's not going to perform as well as if you just had a full, nice piece of concrete to begin with. And I got this photo down here. There is a non-biologically based compound that accelerates concrete healing. It's typically used for waterproofing applications, been around for over 50 years. It is a chemical-based product that produces a crystal. It basically grows crystals within the concrete when in contact with water. And I just wanted to mention that because that is out there. I'm not going to be discussing how that works exactly. That's been around for a long time. We're going to be discussing basically bio-based self-healing concrete. The Zypex is not, one, it's not economic to use in a large structure, and has a lot of other drawbacks. It's chemical-based. It's, it has other drawbacks, but I'm not going to be talking about that. I just wanted to note it here for your awareness. So moving forward. So initially, the pioneering work for self-healing, at least biologically based self-healing concrete, was performed in the Netherlands at the Delft University by a guy named H.M. Jonkers et al. There's a lot of other people working on this research. They started by just quantifying, the self-healing capacity of your ordinary concrete, which we learned, there is some self-healing capacity of any concrete, basically due to, any cement that is not hydrated during the initial set. So you're going to have some of that left over, and if water gets in there, it will react and kind of self-heal, although it's way too slow, and you cannot actually heal significantly sized cracks or deficiencies in a reasonable amount of time using your typical concrete. And they did look into if you increase your, or if you drop your water cement ratio enough, you're going to have more self-healing. But we've been over many times about we want to minimize the cement required due to many environmental concerns and cost concerns. So in order to get any sort of significant self-healing from a regular concrete, the water to cement ratio has to be so low that it's impractical. But in addition to quantifying the original concrete, he also kind of defined and found a species of bacteria that he could put into concrete that would act as a catalyst to accelerate the natural self-healing capacity of the concrete. So this is how it works. This is the chemical reaction. You're actually seeing the calcium lactate is the actual bacteria that was selected to accelerate this reaction. They naturally basically eat oxygen and produce your calcium carbonate. And using this method, as you see, is about 5 times as much self-healing capacity as in a standard concrete. And obviously they had to play with a lot of challenges keeping the things alive, keeping them active long enough to actually have significant self-healing, and then also not impacting negatively the material properties of the concrete. It's still got to be as strong, and it's got to be cheap. It's got to be usable, basically. So, and some of this research actually over the course of the last 15 years since they kind of first started this, they were noticing, some of these bacteria in the concrete actually cause odors. So that's another unanticipated negative consequence that they found over time doing this research. Currently, there was kind of a breakthrough in the technology where in Worcester Polytechnic Institute is Jessica Rosewitz and Associates. Instead of using bacteria, decided to go with a enzyme, which is much more durable. So it doesn't need as much protection from the concrete to stay active and viable for a long period of time. It also doesn't die. So it and is a much smaller molecule. So you can fit a ton more in there, and it's a lot more effective and a lot cheaper and a lot easier to mix, doesn't cause any smell, and actually improves concrete characteristics as opposed to the live bacteria, which had to be encapsulated inside of a clay particle, which had detrimental effects to the strength of the concrete. So this is kind of how it works. I'm not getting too in-depth into the chemical process behind all this. Essentially, as opposed to, it works in the same, using the same mechanisms as the bacteria, except we're basically using an enzyme to accelerate the reaction instead of a live bacteria. And that was a pretty big milestone or breakthrough in the technology that is being researched right now. So this is the areas of future research, what they're trying to do with this new enzyme-based approach. They got to figure out, can this thing be scaled? Is it going to be cost effective? Most of these things are yes. I mean, it's cheaply available. It does not impact strength. You actually add it to the mix water in a very, very small dosage. So one of the key things is actually making sure that your mix water is mixed really well, which is obviously making sure your mix water is mixed well into your concrete mix is something that is important anyway. That's why we've got the big drums rotating on our concrete trucks. This is why we got mixers. So it's not something that there is no new technology required to incorporate this into the concrete, which is a big benefit. yeah, I mean, and that's it. Thank you very much.